So the second meaning of spreading is spreading the technology around the world. Okay, so we came to a realization recently that the techniques we develop can be much more used if they would be more useful. So it's up to us to do it. And I'll tell you about that as well. But the story starts with super resolution localization microscopy. You've all heard about this, so I'll go briefly. Basically, you have a fluorescence image of an object. It has 1 million molecules. They all fluoresce at the same time. You get a resolution that's diffraction limited. So that's 250 nanometers on a good day. You want more than that, better resolution. You make them blink somehow. Here they are blinking. You capture a movie. You localize algorithmically each one of these points. You put a point here. And at the end of the day, and hopefully sooner, you get a reconstruction that is tenfold better in resolution. If you do it well, if you do it early, you get a Nobel Prize. Now, the image analysis story is pretty simple here. You have a point source, nanoscale. You measure this diffraction limited spot, okay, 1 million times, right? But each problem is this. And then you fit this to a model, to a Gaussian. If you have a better model of your PSF, okay, you find the center position or the location of this particle, and you're done. You just have to do it a few times. Okay. In reality, there are problems because you're going to get in an experiment overlapping emitters because you want to do this quickly, the experiment, and to accumulate 1 million molecules quickly, it means each frame will have many molecules. So you're going to end up with a field of view that looks like this. You don't know how many molecules you need to fit here. They are overlapping. So it's a problem. You can't just do this fit. And over the years, people came up with various methods to solve this multi-emitter problem. And some of them were very good. But they are all pretty slow and require parameter tuning and so on. It could be very slow. When we approached this problem, this was 7 years ago approximately, and we realized it's time to do deep learning on this thing, to use machine learning. The logic was, if you can train a neural net to classify cats and dogs, maybe you can train a neural net to tell you where these molecules are, just by showing it many examples. So pretty simple. I mean, nowadays it looks trivial. So we trained this CNN, this convolutional neural network that learns from 10,000 images of randomly simulated point sources with noise, right? To output the positions of these molecules. And after 10,000 images, the next time it sees an image of that looks something like this, it will just spit out the positions. And then you can just feed it the entire movie. You actually don't even have to do localization. You don't need to have a localization list. You can just sum up those images. It turned out over the years that people are interested in localization lists. So, okay, so we can also provide localization lists. But anyway, it works and it's great and it's very fast. And there's a lot of related work on this issue that I won't even mention. Just, I stopped following around here. The interesting part really happens when you go to 3D. So what happens in 3D? This is a microscope. This is a point source. And as it moves in and out of focus, you see the PSF, the point spread function. It's a nice tight spot when you're in focus, and when you're out of focus, it becomes blurry. And of course, we heard about this also. It's a difficult system to use in order to localize something in 3D. Why? Well, first of all, there is some ambiguity. Above and below focus, the PSF looks similar. Okay, that's confusing. And also, there's a very small range over which you see anything at all. The depth of field of a high NA microscope can be 0.5 micron. And above and beyond that, and below that, you're buried in the noise. People came up with many methods to do 3D single molecule localization microscopy. We heard about some of them yesterday, and some of you in the room worked on that. I'm going to talk only about one specific method, which we love, and it's called point spread function engineering. And it works like this. This is a classical example of point spread function engineering. It's called the double helix PSF. The idea is you take this optical element, think of a very distorted lens. Okay, it's actually a diffractive element. Then this is the topology of the element. You stick it in the microscope, normally in as close as possible to the Fourier plane. We heard about the Fourier plane earlier today. And it's a phase element. It acts, for those of you who like signals and systems, it acts as a filter in your linear system. So it's a frequency filter which multiplies your OTF. As a result, you're modifying the point spread function. Okay, and this is the result. You see, instead of a point, you get 2 points and they rotate as a function of z. So now if you just, you could pause this video in principle and you see one of these snapshots and you know where the molecule is in X, Y, and Z. So it's informative, great. So this was developed back in 2000 for single molecule localization microscopy in 2009 by Raphael Piston and W.E. Murner. But there are other PSFs that people have engineered. Here's a few of them. Corkscrew, the phase ramp PSF, self-bending PSF. So these are all different ways to achieve basically the same thing. You modify the PSF of your microscope, some shape that encodes the Z information about the position of your point. And that's a very cool degree of freedom if you think about it. And when I saw all of these designs, I thought, so what's the optimal PSF? Right? If you're allowed to put any filter in the Fourier plane, what do you want to put there to encode most informatively the position of a point source? So it's a legitimate question. And if you, like me, have the tendency to think, if this is the first time you see this, it doesn't matter maybe, right? There's conservation of energy, maybe there's also conservation of information, right? That would be conceivable, but no, it's wrong, because here are some examples. All of these are different, except this is nothing, but these are different phase masks you can place in your system, and they all generate different PSFs. This is the double helix, this is astigmatism. These two are interesting. It's the cubic phase mask and just an extended depth of field phase mask. These two are different from these two because they are Z insensitive. In fact, they were designed to increase the depth of field of a system. And those were designed to encode the Z position. It's the opposite challenge, right? So immediately you see this is a good idea to encode Z this way, and it's a bad idea to encode Z this way. And this means there's a range. Okay, so what's the optimal solution? So if you treat this as an optimization problem, then you need a metric. What are you optimizing? So it is an it's an estimation problem, right? Localization. You measure an image and you have a forward model that tells you if your emitter was at XYZ, you would measure this. Okay, but you're interested in the inverse problem. So it's this kind of an optimization problem, an estimation problem. And as we heard yesterday from Francisco, there is a very useful quantity called the Fisher information that tells you how informative your measurement is to the parameter that you're trying to estimate. In our case, this translates to a shape that would change a lot if Z changes a little. And so you're looking for something like this. The nice thing about Fisher information, you can calculate it. You just need a likelihood model. In our case, it's Poisson noise, and the mask that you're trying to test. And you can use this as an optimization metric. So you optimize it over some predetermined range. I'll skip the details. It's numerical optimization that's irrelevant for today because this was 11 years ago. But the end result is this. Nice looking tetrapod phase mask, and this is the point spread function. So this is the PSF that maximizes the Fisher information of estimating XYZ position of a single emitter. Great. So, by the way, this is under the constraint of low photon numbers, right? So you put in the realistic conditions of your system, and this is the result. So you can do 3D SMLM now, right? You can blink molecules, fit each one to the model, and then you get a 3D reconstruction at super resolution of your image, of your object. And this was done. This has been done, not by us. And they used the tetrapod. And that's great. What is the challenge? Overlap. Okay, so you see this takes a long time to acquire this image because you have to make sure these shapes are not all over each other, because then you have a very difficult fitting problem. It's an image processing problem. This is easy. This is difficult. Okay? So what's the solution? Well, you already can guess. A neural net that is trained on simulation. We have to have a very good model of our optical system. Okay, so we do. And then we can simulate images that look like this. And the neural net now, it's a more complicated one because it outputs a volume, occupancy volume, many zeros and ones whenever there is a molecule. And that works. And here is an example. This is a blinking SMLM with a tetrapod. The Z range, by the way, I didn't mention this. The Z range of this phase mask is something like 5 microns, which is much more than astigmatism, which would give you like maybe 1 micron. Okay, so for mammalian cells, for example, this is relevant. Anyway, you see in gray the blinking, the raw data. In purple, you see what the network understands from this. So that's the fitting that's happening. And at the end of this analysis, you get a 3D reconstruction of mitochondria, which is what was imaged here at something like 50 nanometer resolution XYZ. Of course, the idea works with any PSF. This is with the double helix using deep storm 3D. Okay, this nice reconstruction. And then you can ask yourself, okay, I told you that this tetrapod PSF was optimal for localizing a single point source with the Fisher information, right? That's how we derived it. But we don't have a single point source in these experiments, right? They are overlapping. Maybe it doesn't make much sense to use such a big PSF with overlapping emitters, right? So what is the optimal PSF to use in this case? And here is where, you know, AI is making us stupid. You know that, right? So here is it's also making us stupid in the sense that we don't even have to come up with an optimization metric. Okay? What do I mean? Let's say that my end result is a PSF such that at the end of my experiment, I would get as many localizations as precisely as possible. Okay? How am I going to do this processing? With a neural net. So this means that as I train the neural net to do the decoding, I can add a layer that does the encoding, the optical encoding. And so while the net is learning to reconstruct the images, it also learns how to encode them optically. And it will tell me what phase mask I should use. And if you do that, this is the net learning. It's actually the optimization process is learning the optimal optical encoding. And it's becoming this spiral shape. This is the phase mask that the network really likes. This is the corresponding PSF. And so the network instructs us to go ahead and fabricate this and do this experiment. So, okay. So we do it. It kind of looks like a hummus plate. So before lunch, right? It's a good time. So this is indeed a smaller footprint PSF, so that makes sense in retrospect, right? And it works. These are telomeres. We can count more of them and more precisely when we use the hummus compared to this tetrapod. How do we know it's more precise? Because this is a fixed cell, so we have the ground truth and we can compare. Right. People used to ask me, is it worth it to split your detection path into 2 and use 2 different phase masks for some reason? I used to say, I don't know. But now we do know that, yes, in some conditions, it's worth it. Okay? When you have very high density of emitters, and so if you only use one PSF, they would hide each other in some configuration. But then if you could only take another image with another PSF, then these two will not hide each other anymore. So it's more informative. Of course, it's more informative to measure something with two different PSFs. But is it worth the SNR? Because you split it into half and half, right? So each channel is split. So at very high densities, it is worth it. And the nice thing is when you let the network learn two different channels, it learns these highly complementary PSFs, right? Because it's allowed to use, for each emitter, it sees it twice, and it uses these two channels to tell you where it is. And if you superimpose these, you see how nicely complementary they are. We never asked the network to do something complementary, it just came up with it by itself. Interestingly, Matt Lu thought about a very similar idea rationally many years before that. But this is the corkscrew PSF. It just came up with a similar solution. Yeah, so you can do that. Another degree of freedom we have, by the way, I just want to stress something. In biplane microscopy, you have this automatically. You already have two channels, right? So it makes sense to think maybe you can improve biplane with such a method. Anyway, another piece of information we're interested in emitters is their color, right? Multiplexing, red, green, okay, great. And here is a mask that is learning how to optimally classify, different point sources according to their color. What happens is every optical element you place in your system has some chromatic aberration, chromatic dependence, and phase masks are not excluded from this, right? So if you have one mask here, this is a liquid crystal SLM where we implement this voltage mask, and every color sees a different phase mask just because of wave propagation. It goes like 2 pi over lambda times the optical distance. So you get a different PSF. And here is a snapshot of quantum dots of different colors. They look different, right, because of this mask. And so we can classify them pretty well. And this is on a single optical channel. So no filtering, no spectral filtering, and so on. I want to exemplify the power that this approach really gives you. This is this liquid crystal SLM where we put the voltage mask, right? And this is the phase response as a function of voltage. That's how this device operates. You put a voltage on a pixel, and then light experiences a different phase delay because there's a liquid crystal that rotates. And so the refractive index effectively changes. So, but anyway, red color experiences one phase delay, and green experiences a different phase delay for the same voltage. And this is what allows us to encode color in these shapes. But how much freedom do we have? So to answer that, I will show you an example. And here is an example. These are two fluorescent beads. One of them is green, one of them is red. Okay? But we're imaging them on an optical channel without spectral filter, so they look the same. Okay, there's a filter for the laser, but no green-red filter. They look the same pretty much. We put this voltage mask that doesn't look like anything, but it is. And we measure this. So for someone who sees this for the first time, this is unbelievable, but it's true. There's no Photoshop here. This is what you can see with your eyes. So it's true, and there is related work, by the way, that was done on this kind of encoding, not for single molecules, by Alex Gisacho. We'll hear from him in a few days, and from the Stalinga group. Anyway, we took this to SMLM. If you put this this voltage mask, and then this is the PSF for red, this is the PSF for green, you can look at the fusing particles and immediately say, this is red and this is green. And I also know where they are in 3D because the shape encodes it. How do I know this is rotated diagonally, this is not? So there's this kind of freedom here. This is another one of those masks we actually fabricated by 3D printing. I'll tell you a bit about that in a second. Now, all the time we spent until now was in the Fourier plane, in the sense of this is where we place our mask. The reason for this is that it makes a lot of sense to place a mask in the Fourier plane because you end up with a convolution system. So that means your point spread function is shift invariant. A point here would experience the same PSF as a point here in your field of view. Okay, so it's one less thing to worry about, right? So you just x, y, it's invariant. But it also limits you if you implement this way. Let me show you an example. This is a bunch of beads embedded in a gel. And some of them are in focus, like these two, and some of them are out of focus, right? Can we focus on all of them at once? So if you're trying to focus by moving your objective, then no, right? Because now then these will be out of focus, okay? Can you put a phase mask in the Fourier plane that will focus all of them? Also, in principle, no, because it will just add some quadratic phase to defocus these guys, but then these will be defocused and so on. If you step out of the Fourier plane, you can do it, okay? And here is an experimental example of all of these guys in focus. And again, this was only done by moving from the Fourier plane. And this diagram actually shows you why you have to do this. Because as long as you're in the Fourier plane, all of the light from, no matter where it comes from, it passes through the same circle. But here you can already do some spreading of the information around. So you can do FOV-dependent focusing, field of view dependent focusing. You can go crazier than that, of course, which is more fun, like designing these letter-looking PSFs, A, B, C, D, as a function of where you are in the field of view. If you could think of any use for this, let me know. We heard a bit about dynamics in these last few days, and it is really an important problem, especially now when SMLM in live cells, as we were saying, is becoming possible. Okay, so this is an important problem in terms of signal processing. Okay, again, let's say you can blink in live cells, that's fine, but then you also have to make sense of these blinkings, right? So, and that's not trivial, because in SMLM you have to accumulate images and build a single image. And if you're accumulating images of something that's moving, then you'll get a mess. So what do you do? So we addressed this problem a couple of years ago, and I'll show you how. First, in a demonstration, this is blinking in our lab. You see, as the microtubules are blinking, the student Alon was rotating the camera with his hand, only for the purpose of this demonstration. So you see these fiducials, aggregates, whatever they are, they move, right? They are rotating. If you just sum these images, you get motion blur, right? Because you sum things that were at different positions. So it's not a good idea. Yeah, and it's not just, you can't fix this with drift correction, because it's not lateral motion. I mean, unless you add rotation to a drift correction, but never mind, you understand the point. Let's say this was a live cell, okay, as you will see soon. The question is, can we do blinking SMLM video to super resolution video, right? That's what we really, really want to do. The problem is that it's an impossible problem to solve, because you get information from the molecules that happen to blink in this frame, but all the other ones that didn't blink, you don't see them, and then they moved, right? So there is not enough information in your movie to recover a movie. So we did the only thing you can do in such an inverse problem, which is to assume some prior knowledge. And now it's always a game of what prior knowledge can you assume that is correct? That's number one. And number two is how to use this prior knowledge. Those are the two things that you need to solve a difficult inverse problem, or to try to solve it. So in terms of what we know, so we assume we know what we're looking at, in the sense that we labeled microtubules, okay, so we know it's microtubules or mitochondria. And we assume smoothness of the motion. Okay, so it's not gonna jump very drastically. If you assume these things, now all you have to do is figure out how to use these assumptions, and we did it using neural net. It's a recurrent neural net. It's called a long short-term memory cell, and it's recurrent, so it's a recursive net. And so that's kind of a way to analyze video or audio signals that have temporal correlations. We trained this on simulations, very, very simple simulations, like drawing lines that move around and rotate. So no fancy shapes, but I have to qualify. We are entering now a regime where we are imposing quite a lot of prior information. We have to be careful. Until now, all the locations of the molecules that we were simulating were completely random. So there was no fear that the net would learn some structure. But now there is definitely such a fear, so we have to be very careful. Nevertheless, after we are being careful, we can run it, the network, on data that looks like this and recover this. This is dynamic. It's hard to see, but these microtubules are in a live cell and they are moving. Here it's more visible. This is mitochondria. And from images like this, you get movies like this. So of course, there is information you injected here that of what you're looking for. But it generalizes pretty well. For example, the training data never included a ring, but it figures out there are rings here. So that's one example. Okay. Now, I was once at a great talk by Jörg Beversdorf. It was in MiFoBio 2025. It feels like it was yesterday. And it was yesterday. You see this watermark, right? Here. This is a screenshot that I took during Jörg's talk yesterday. And the reason is this. I'm not sure these are, precise estimates of how many systems are really existing in the world, but I think it makes sense to me that this is the right order of magnitude. And what I'm trying to show here is this. Most commonly used 3D imaging systems today, astigmatism is very common, and double helix, or more generally, PSF engineering, is not very common, okay? And considering how cool this is, you would think, why, right? Why? Why isn't PSF engineering more popular? So I will tell you what I think and how we're trying to solve it to improve the situation. But to summarize my thought, it's partly because it's expensive and or complicated to use. And we're trying to solve both of these aspects. In other words, the elephant in the room is, can people actually use the tools we are developing? We need two things to make them more useful. One is hardware. We need specifically cheap, accessible phase masks, because that's where the magic happens. And those are the parts that are hard to come by. And we need software. We need easy to use, one-click algorithms. In my vision, if somebody needs to install a Python package, we failed. Now, we're not there yet, okay, but I think this is the direction. There are two approaches to this. Some take the approach of we need to educate the public and make the public know how to use tools. The other approach is just make it as simple as possible. The public has other worries to worry about in their experiments. And I subscribe to the second one. Let's talk about the phase mask. What is this thing? So, as I said, it's an adoption barrier for this technology. This is a piece of quartz that is etched with photolithography. It has to be very, very precise because you are playing with the phase of light, and light has a wavelength of hundreds of nanometers, so this has to be on the scale of tens of nanometers, and that's difficult to fabricate. You can also implement it using a liquid crystal spatial light modulator, phase mask, as I told you, but this has its own limitations. It's cumbersome. You throw away 50% of the light if it's unpolarized, because this works only for polarized light. So we figured we have to come up with a simple way to fabricate phase masks. This is after weeks of my students spending in the clean rooms and thousands of dollars we spent to ordering these kind of elements from companies. And we came up with a way to 3D print them. And now I'll tell you why this is surprising that it could work and why it does work, and then it won't be surprising. So what is this dielectric phase mask? It's actually something like the skyline of a city, but very tiny. This is what it looks like under a good microscope. These features, again, are tens of nanometers or hundreds of nanometers of transparent material. And if we zoom in onto two of these pixels and think what's really happening here, then you have your plane wave coming in, And then after propagation through this element, there is some relative phase between these two pixels. Why? Because their thickness is different. That's it. And it's 2 pi over lambda times delta n times this thickness. Delta n is the refractive index of glass minus refractive index of air. Okay, so it's very easy to calculate. It's very easy to see. And then this happens tens of thousands of times for all the pixels at the same time. And you get your phase profile. And now look at this. Delta n times delta t comes in, right? So if you could potentially decrease delta n by a lot, you could increase dt, the thickness, by a lot, and end up with the same numbers. Okay, what does this mean? It means instead of putting glass in air, you take polymer 1, polymer 2, with very, very close refractive indices, and this allows you to scale up dt by the amount that you were able to decrease delta n. So if delta n is now 0.005 instead of 0.5, then that's 100-fold, right? Yeah. Then dt now can be 50 wavelengths instead of half a wavelength. And that is something you can easily fabricate in your lab if you just have a pretty good 3D printer, consumer grade 3D printer. So that's what we do. Basically, this sandwich of two polymers, and we can fabricate these 3D encoding masks, 3D printed masks. So we fabricated a bunch of these and sent them around the world. This is a double helix mask and the data from it that we sent to the UK. This is a vortex plate we sent to Tel Aviv, another vortex plate to Göttingen to use in a STED setup. And they work, they're very easy to fabricate. And so, yeah, and that's, we keep on improving this method also to the point that right now, to fabricate a phase mask, from the moment you want to have a phase mask to the moment you're holding it in your hand, takes 10 minutes. So it's really, for anybody who has ever done any lithography, this is unbelievable. And it happens in your lab, not in a clean room. Okay. Another way to make life easy when you're doing this kind of work of phase of PSF engineering is to get rid of the 4F system. So I didn't mention this, but when you do PSF engineering, you need access to the Fourier plane. The Fourier plane is often inside your objective, which is not an easy place to do anything. So people build an extension by two lenses. It's called the 4F system. And in between, you have this Fourier plane, and there you stick your phase mask. So it's fine if you can do it, and if you have someone to build this little setup, okay. And if you have the room to accommodate for it, but sometimes you don't. For example, in this kind of setup, this is a high throughput microscope with collaboration with Sartorius, it's the Inksight. And it just has this objective that keeps moving around and scanning these wells. And there's no place to fit a 4F system in such a setup. So we came up with a way to just attach the phase mask, as you saw here, to the bottom of the objective and just place it here, and that's it. And you have your objective with engineered PSF. The phase mask is simple to fabricate, so everything is very easy. What this allows you to do is stuff like that. What you see here is a spheroid. It's a cancer spheroid. Some of the cells their nuclei are fluorescently labeled. And this is an encoded image. This is already with a tetrapod PSF. This is not single molecules. It's just some crazy shape. If you train your neural net on many such spheroids, you can recover actually the 3D positions of these cells from a single shot and no longer point sources. And we're taking this to be much more simple now. So again, printing the mask, printing this adapter, sticking this under a Nikon objective. This is for a TIE, I think. We also have adapters for Olympus, the same idea. And that's it. You have your 3D encoding in your microscope. So it's becoming very simple. Now, when you do something like this, one of the things you have to worry about is, So by the way, this is just blinking molecules using this thing in a microscope in Mike Heilman's lab last month or a few months ago. When you do something like this, you do have to worry about field dependence because you are not sticking your mask really in the back focal plane. As I mentioned, for high NA objectives, this would be inside the objective. But okay, so you're not in the Fourier plane. Who cares? Well, we care because there is field dependence. Okay, so the PSF in the center doesn't look like the PSF on the sides. But so for a low NA, that's pretty much fine. For a high NA, it's more problematic, as you can see here. But, and this is something that's happening in these years, right? We don't worry about this so much because we can compensate for that algorithmically to some extent, right? And many people have been working on field of view dependence PSF calibration. So this is their time to shine because now there is a motivation to do this, you know, for this simple system. In the last few minutes I want to talk about democratizing the algorithmic part. Okay, so I talked about democratizing the phase masks. They're easy to make, right? But what about the algorithms? So what is the problem with these deep learning-based SMLM algorithms analysis? The problem is this: the network is trained on simulated data. The simulated data has to resemble your experimental data. And the more it looks like the experiment, the better everything is going to work. If it doesn't look like your experiment, it's not going to work well. So a lot of effort has to be put in to make your simulation look like the experiment. And this is a very manual and time-consuming step. So automating this is not just nice to have. It could really make the difference between a useful tool and a useless tool. Because if you want, and I'll show you the pipeline, and then you'll understand. So this is the DeepStorm 3D pipeline, but it's actually pretty similar for other algorithms like Decode. So basically, you need a calibration measurement of your PSF. This is done usually on a bead. Nowadays, there are some approaches that can figure out the PSF from the blinking data itself. Okay, great. And then you do something like phase retrieval to figure out what the mask that you actually have there, including the aberration in your system, is. And now you are, in principle, ready to simulate point sources in your system in 3D. Okay? So you do this, you need to take care of the background, of course. You start simulating images that look like this, and then you sit there, you see this image, you see your experimental images, and you go like this, and you hope it looks the same. If it doesn't, you go back and iterate and change the parameters, the density, the SNR, the Z range, everything. And that's very time consuming. It's very, requires expertise and so on. And then you run your analysis and you wait. Okay, and then your inference frame by frame and you build the image. We automated all of this, which makes a big difference. It's called Auto DeepStorm 3D. It's a nice GUI. You can do one click with some like reasonable parameters, or you can still play with the parameters, of course, to make it better. Basically, yeah, so it takes a movie, it understands the parameters from the movie, so you don't have to go back and forth. One click, you get reconstructions. This is just to show that it's equivalent to DeepStorm 3D in terms of performance on all kinds of PSFs this was tested on. So to compare the times, you know, to run DeepStorm 3D and get this takes 14 hours plus who knows how many hours or days, depending on your expertise, to play with this data. And this one click, less than 2 hours, and it's mostly the inference time and generating the training data. There's one small factor of improving computation efficiency, but that's not very important now. I won't go into it. It works with other PSFs as well. I just want to finish with 2D. So when you do SMLM analysis in 2D, which is most SMLM analysis, you run, using deep learning, you run into a similar challenge. You have to match your simulation to experiment. So we automated this as well. But here we can do another extra thing. The point spread function in 2D is very similar across different microscopes. Okay, it's basically a Gaussian. No offense to people who model PSFs in 2D. But the point is, if this is the case, it means you can pre-train the networks. Okay, you don't have to acquire data, then train a network based on what your data looks like, okay, and which takes a lot of time, and then run inference. You can pre-train networks under different conditions, which is what we did. We train a bunch of networks for high density, for low density. It's already trained. Now you measure your data, and automatically it's directed, each patch is directed to the right network, because the algorithm understands your SNR condition, the density, and so on. And then it runs on the whole thing and reconstructs it. You might think, wait a minute, what if I have a different pixel size in my camera? What if I use a different wavelength? So to a pretty good approximation, we just scale the experimental images accordingly. You resample them on the right grid according to the pixel size of your camera. And so you don't need to retrain anything. You just modify the experimental data to look like the training data. And then this works. The nice thing about doing it in patches is that, different patches in the field of view are different. It makes little sense to use the same network for this patch and for this patch. Why? So you can direct now different patches to different networks. They were all pre-trained. It works better than not doing it. This is this image. Yeah. And that's it. I will summarize now. So I hope I convinced you PSF engineering is an efficient way to encode extra information like depth and color. The delegation of post-processing in recent years to deep learning, beyond making us all stupid, it also enables unprecedented freedom in microscopy design. Because the image needs to be informative, not sharp. It's a different way of thinking of how to design an optical system. Finally, phase masks can now be printed using consumer-grade 3D printers. Physical dimensions of tens of microns correspond to optical quality of tens of nanometers. I have one of those phase masks with me in my bag. And if you want to see it, let me know. But more importantly, if you want a phase mask, let me know. Email me. We love to share our phase mask with people. And we'll talk about how to do it, how to analyze the data. And we love to collaborate on these things. Finally, I would like to thank the people who did the work, our recent collaborators and funding, and thank you for listening.
Thank you for this really nice talk. I'd like to ask you the first question. I did some astigmatism, trying to do some 3D tracking, but when doing it in live and using fluorescent proteins, it's tricky because you spread the signal into the different PSFs, so exposure time has to be quite high to do tracking and follow dynamics of proteins. So how does this approach compare to the classical astigmatism in the sense of capturing the brightness and yeah.
So astigmatism is a form of PSF engineering, right? It's just a special case of PSF engineering. It's actually a pretty good case of PSF engineering. For if you're interested in a small Z range, say 1 micron, then I would say do astigmatism. It's great. It has a small PSF, so the footprint is small, the photon efficiency is good, it's simple to implement, just do it. So I can only ruin your experiment further if you're interested. But if you have a larger Z range of a few microns that you need to track something, then astigmatism will not work anymore. Then you have to get clever. And then one of those masks maybe is a good solution. Okay, but spreading the photons is bad, right? You don't want to do it only if you have to do it.
Okay, yeah, makes sense. And also I wanted to ask you, what is the longevity of these masks? Like how long can you use them
for?
The
3D printed ones?
Yes.
Well, we started with this a few years ago, and none of them have been destroyed yet. So at least a few years, I guess.
Okay.
But it depends. You don't want to heat them too much, right? So it's not for high power applications. So, but on the imaging side, no problem.
Okay. Nice. Thanks. Questions from the audience?
Yes, so a little bit of a follow-up on this question. So you nicely showed that you can optimize the phase max as a kind of function of localization density. Do you have to optimize the phase mask also as a function of the probe that you're using in general?
Well,
in the sense that if you have like a fluorescent protein, which is kind of low brightness as compared to high brightness
yes.
probes, I imagine you have to take into account the spreading of the photons. So how do you deal with this?
That's right. So the parameters that are important for which a PSF is going to emerge as the optimal one are the brightness. Mostly it's bright SNR and SBR, how much background you have. Let's take the extreme case when you have infinite photons and no background, then this becomes a very boring problem and it doesn't matter what mask you use. But once you start making it more challenging, then yes, the solution would like to shrink your PSF as much as possible while still maintaining some Z. Okay, and the Z range is important, over which Z range you want. Intuitively, yes. If you have low signal or high background, then it will produce smaller PSFs and PSFs that are less crazy looking, because you can't say it will catch on some schmutz on the side when it's just noise, right? So yeah. For what? If you have okay, so if you have a fiducial bead you want to track in 3D and it's isolated, tetrapod. If you're doing SMLM high density, then hummus. Yeah, that's a good question. I think it makes sense to beautify them. I think it makes sense to smoothen them. It comes down to how much you trust this. It comes down to how much you trust your model, right? Because I think beautifying them or smoothing them a bit, or so making them more robust, means that your model doesn't have to be that precise, which is always the case. You're always going to have aberrations, and your pixel size is a bit different, blah blah blah. So I think it does make sense to beautify them. We haven't tested it. It would be a nice work for someone to try. There's someone over there in the left.
Hi, thank you for this talk. You mentioned my question is mostly on the deep learning part. So you mentioned that you generate some images for your training set, and I was just wondering what do you use actually to create those images, and is it a GAN or?
How do we generate these PSFs, these images of randomly positioned PSFs? Used to be MATLAB, now it's Python. Or you mean the imaging model?
Yeah, the model.
We have a pretty good model of a PSF in a microscope. So you give it X, Y, Z, and wavelength, and pixel size, and everything, and it tells you and the phase mask, and it tells you what the PSF is going to look like. Just by propagating through the model. There's another question.
This is working. Hi, Yoav. Thanks for the great talk. I think we have some 3D printers here. So do you think we can print some face masks and try them out at MIFOBio?
If we also have the right resin, then yes. I doubt it. I didn't bring any resin. I didn't bring any polymers. So that would be a limiting factor. Unless they have in the SPAR here, I don't know.
We can check.
Maybe we have time for one more question.
I'll be quick. It was just about the 3D printed phase masks. Have you tried excitation shaping as well using these masks, or only on the emission side? Do you think they'd survive? You mentioned a bit about the laser problem, but
Yeah, you mean if we place the mask on the excitation path of, say, a confocal or something,
well,
or for SIM, or
thinking more towards like light sheet applications where you
light
use
sheet,
making
yeah.
propagation variant beams.
Yeah. Do you know what the temperature differences are in this plane? So it comes down to that. I don't think power is that high that it will become a problem, but I'm not sure. We have to test it. If you're interested in testing it, then let's talk.
Awesome. Thanks very much.